In this video, we're going to talk about reciprocal frame vectors for curvilinear coordinates. In a parameterized space, where we'd say we have an A and B parameter, and there's some surface that's defined by that space, we can form the tangent vectors x sub A and x sub B with respect to the vector x sub A at AB, where we say that x sub A is the derivative of the vector x, the position vector x, with respect to A, and x sub B is the derivative with respect to B of that position vector x. And the problem that we want to solve today is how to find the reciprocal frame vectors. Those are the vectors that they're x upper A, x upper B, and so forth, that are all within the span of our tangent space that satisfy this particular condition. This is the reciprocal frame vector condition. So these x sub i's that satisfy these relationships, those are our reciprocal frame vectors. So one question of why do we want these is because they answer the question of how do we compute coordinates. We know how to compute coordinates of a vector with respect to a standard basis. So suppose we have x. We know that we can decompose x into the sum of x dotted with the orthonormal basis vector ei times ei, and we sum over all I equals 1 to n, say. So how do we generalize this to cases where our EIs here, our EIs, this decomposition required that our EIs all be orthonormal. So both all mutually perpendicular plus all unit vector length. So that might be the case where you have, say, a cylindrical coordinate system. So you can have a pair of mutually perpendicular vectors at any point in the space. So, if we have a spherical coordinate system, we have a unit vector outwards, we have a set of mutually perpendicular vectors that are all mutually perpendicular. In both of these cases, we don't have in the cylindrical case and in the spherical case, we don't necessarily have perpendicular vectors. Or we don't necessarily have unit vectors at each point. So for example, let's say we have cylindrical. So in cylindrical, YL cylindrical, there we have our vectors are x equals e1 e to the I phi, let's say r plus z e3. So here I've said I equals e1 times e2. This is a geometric algebra parameterization of the cylindrical coordinates, of the cylindrical position vector. You could do that in standard coordinates if you felt like it. So in this case, let's look at what our parameters are. So we have x sub r is e1 e to the I phi, x sub theta, or I've said phi in this case, x sub phi is going to be r e2 e to the I phi, and x sub z, and these are all vectors, will be, not z, but the derivatives of ze3, which is just e3. So our x sub r and our x sub z are all our unit vectors, but our x sub phi is not. So I want to say, how do we generalize this to where we have orthogonal vectors that are not necessarily unit vectors? And that's pretty clear how to do it. All we have to do is we have to write, let's say, instead of x, which is our parameter, let's say we have an arbitrary vector y, and we want to look at the components of y. So y dotted with x sub alpha, say, and that would be times x sub alpha, but we have to divide by the length squared of x sub alpha. So there's a generalization for vectors that are, we have orthogonal unit vectors, and we want to decompose a vector with respect to orthogonal unit vectors, and we can do that fairly simply. Now, one thing I want to note here is that this here is essentially our reciprocal frame vector for this particular coordinate system. So, and observe that it is just 1 over x alpha, because 1 over x alpha is, well, if we multiply 1 over x alpha is just x alpha times its length squared, or its dot product squared. So strictly speaking, 1 over x alpha is x alpha over x alpha dotted with x alpha. So if we dot that again with x alpha lower, we get 1. So we see that this satisfies x alpha dotted with x alpha equals 1. That's the delta ij for I equals j case. So we can summarize this by saying, so if we have orthogonal vectors that are not necessarily orthonormal, then we can write any vector as that vector dotted with our basis vector times 1 over that basis vector. And in this case, 1 over our basis vector is just our reciprocal frame vector. So this is just x alpha. And then we have x alpha dotted with x beta equals delta alpha beta for all alpha beta over the parameters. So this tells us how we compute coordinates with respect to an orthogonal frame. And in fact, it happens to be how to compute coordinates with respect to any frame. So let's see why that works. So if we suppose that y is some sum of y, let's say yi, xi, where xi's are our basis vectors. And now let's dot this with xj. So what do we get? We get yi, xi dotted with xj. But that is just the sum of yi delta ij if our xj's are reciprocal frame vectors. And so that is yj. So we see that y equals y dotted with xi times x lower I. So we found a way to compute the coordinates of any vector with respect to an arbitrary basis vector, provided we can find xi dotted with xj equals delta ij. So if we can find our reciprocal frame vectors that satisfy this condition, then we can find our coordinates. We can also decompose the vector in terms of the reciprocal frame vectors. And so let's say that y is some y lower I times x upper I. Well, then y dotted with x lower j is yi x upper I dotted with x lower j, and this is just delta ij, so we get yj out in the end. And so we can now say what our vector is yi xi, or y lower I, x upper I, and here our yi is just y dotted with our reciprocal frame vectors, and our y lower i's are y's dotted with our basis vectors. So here is the general decomposition in coordinates of an arbitrary vector, where our coordinates may be orthonormal, they may not be orthonormal, they don't even have to be Euclidean basis vectors, but provided we can find the reciprocal frame vectors that satisfy xi dotted with xj equals delta ij, then we have a way of computing the coordinates of an arbitrary vector. All right, so let's look at some examples. So we looked at the example of cylindrical coordinates. We could let's do elliptical. So if you have an elliptical coordinate system, z, let's say this is a, and a epsilon in that direction, and a theta angle here. So our position vector for an elliptical coordinate system would be a E1 cos theta plus a epsilon E2 sine theta plus Z3. So if we look at our XA is just E1 cos theta plus epsilon E2 sine theta, and our X theta is A times minus E1 sine theta plus epsilon E2 cos theta, and our xz is just E3. So there's a elliptical cylindrical-like coordinate system. So if we were to draw out our vectors at any point in space, we would see that we have XA and X theta, and we find that those are orthonormal only at these points here at multiples of pi by 2 for theta equals pi by 2. So at any other point, this is not a right angle. So a right angle might be here. So our XA dotted with X theta is not equal to 0. So how do we compute our reciprocal frame vectors for something like this? So this is an example showing that it's not trivial, and we have to figure out how to do it. And let's go and figure out how to do that. So our problem is defined xi dotted with xj is delta ij. And we know that our xi is in the span of our basis. So that means that xi might be, let's look at a two variable case specifically to start with. So let's say that we're looking at x equals x of a, b, and we have x of a is dx dA, and x of b is dx dB. You can think of this problem as a general problem given xa and xb, and they don't have to be curvilinearly derived like this. But so if we have these, then we suppose that xa is some, let's say alpha 1 xa, x lower a plus alpha 2 x lower b. So that's our x upper a. And we can suppose that our x upper b is, let's say, beta 1 xa plus beta 2 xb. We want to solve this system given our constraint. So this formulation of the linear system to solve builds in the span criteria for the reciprocal frame vectors, which is important. And then we want to impose the constraint here over xi xj equals delta ij. So to impose that constraint, we just form all the dot products. So we have xa dotted with xa, upper lower, that will be alpha 1 xa squared plus alpha 2 xb dotted with xa. And that equals 1. Now we have xa dotted with xb. And the alpha 1 xa dotted with xb plus alpha 2 xb squared equals 0. And we're going to do the same thing for xb. xb dotted with x lower a is going to be, now we have beta 1 xa dot xb and plus beta 2 x. Do I have these right? I do not. That is xa, so that's xa squared plus xa dotted with xb, and that's 0. And now we have xb dotted with xa, and that is beta 1. Sorry, xb dotted with xb, xa dotted with xb plus beta 2 xb squared. And as always, I'm writing for a vector a squared is a dotted with a. That's a geometric algebra contraction axiom. That's also very handy shorthand. All right, here's our equations to solve. Now we notice that the kernel of this linear system is the same in both cases. So we'll just write this as a matrix equation. So let's say D is xa squared, xa dot xb, xa dot xb, and I'm flipping the orders here because it doesn't matter, and xb squared. So now our system to solve, and let's write alpha is alpha 1, alpha 2, and beta as a vector is beta 1, beta 2. And I've put my signs downstairs, or my indices downstairs, but that's not really going to matter. So our system to solve is going to be d alpha equals 1, 0, and d beta equals 0, 1. So that's our system. D alpha equals 1, 0, and d beta, these are coordinate vectors, equals 0, 1. Let's invert D. So D inverse is going to be 1 over the determinant of xa squared xb squared xa dot xb xa dot xb times xb squared xa squared minus xa dot xb and minus xa dot xb. If we go and multiply these out, we should get xb squared xa squared minus xaxb squared is the determinant. Xa squared xb squared minus xaxb. Okay, that's good. And another check, looking at this, say this row times this first row times first column times the second row, then yes, we get 0. Okay, that's got the signs right and the positions right in my inverse. So we can now form our alpha 1, alpha 2, and beta 1, beta 2 is D inverse 1, 0. 1 over the determinant of D times, and we multiply out by 1, 0, we get this first column. xb squared minus xa dot xb. And here we have D inverse 0, 1. Just going to pick up the second column, 1 over the determinant times minus xa dot xb xa squared. All right, so now we can write out our reciprocal vectors. We had xa, which was let's say xa is alpha 1 xa plus alpha 2 xb, which is minus xa dot xb times xa plus xa squared xb all over the determinant, which wasn't written out explicitly, but is xa squared xb squared minus xa dot xb all squared. There's our first reciprocal frame vector in 2D, or for a two-dimensional parameterization, two-dimensional manifold, and our xb. Oh, and I mixed this up. I just read off these coordinates here, x, so that was our xb, beta, xb. Our xa has xb squared, xb squared xa minus xa dot xb over that same determinant. Okay, so here's our reciprocal frame vectors for a 2D parameterization, and so xa squared xb squared minus xa dot xb all squared. Okay. So can we tidy this up? That is the next question. And I'm going to look for the geometric algebra form for this set of relationships, and that will distinctly tidy this up. First thing we're going to note is this denominator may look familiar. And the specific way that it might look familiar is that's the square of a bivector. So we write out, let's say we have a wedge b squared. That's the same as a wedge b dotted with a wedge b, which we can use the distribution identity to write as a wedge b dotted with a dotted with b, and go and compute each of these in turn. So that is a times b dotted with a minus b times a dotted with a all dotted with b, which is a dot b squared minus b squared a squared. So that's the square of a bivector has this specific form. So we see that the denominator is the square of the xaxb bivector. So if we have the form xaxb, then that beastie is just xa wedged with xb squared, but minus. And how about the numerators? Are these numerators also, do they have the form of some sort of bivector dot product? And we will see that they do. So let us rewrite this. So I'm just looking at the signs here. I'm going to just refer to my notes for this, for rewriting, so I don't get the things mixed up. So I'm going to start from scratch here. Where's my pen? There, okay. So we have xa as x b squared xa minus xa dot with xb times xb all over minus xa wedged with xb squared. And our xb is minus xa dot with xb times xa plus x a squared xb all over minus xa wedged with xb squared. We're starting to get some structure here. Now we can notice that this guy up here is a dot product, and this is also a dot product. So let's write that out. And so let's try it here. So if we try, let's try xa dotted with xa wedge xb. What is that? That is xa squared times xb minus xa dotted with xb. So doing inner times xb, outer times xa. And do we have that term anywhere? So x, we do. We have xa squared xb minus xa dot xb xa. So now we can write out xb. So xb is minus xa dotted with xa wedge xb over xa xb. And I brought the minus up from downstairs in this. All right, and so that is xb and xa. So that's what happens if we take xb dotted with xa wedge xb. That is, so inner xa dot xb times xb minus outer is xb squared times xa. And we have that. So we have the negative of that. So the negative will cancel with this negative, and we're going to be left with xb dotted with, say, wedge xb all over xa wedge xb squared. Okay, cool. So we're getting there. We almost have this in a nice tidy form. We can tidy this up a little bit because if we have, so this is just a scalar on the bottom, we can put that scalar in with our bivector, and then if we have a bivector divided by a bivector squared, that's just the inverse of that bivector. So we can finally write xa is xb dotted with 1 over xa wedge xb, and xb is minus xa dotted with 1 over xa wedge xb. That's the geometric algebra form of the reciprocal frame vectors for 2D parameterization. This is our final form. Let's see why that works. So if we want to look at why this works, let's form xa dotted with xa, say. So if we do that, we have xa dotted with xb dotted with 1 over xa wedge xb, which, once again, here's our distributed form. This is a bivector. Bivector dotted with a vector dotted with a vector. That is just the bivector. That is the same as xa wedge xb dotted with the inverse of xa wedge xb. And what do you know? We have 1. Okay, so, and similarly, if we have, let's say we take xa and dotted with xb. Well, we have xb dotted with xb dotted with xa wedge xb, which is just xb wedged with xb dotted with 1 over xa wedge xb, which is 0. And 0 because xb wedged with xb is 0. We found our reciprocal frame vectors through algebraic means just by solving the linear system. And now we see a structure that really makes sense in terms of the distribution identity. And we see that this can be easily generalized to higher order parameterizations. And let's show that. So if we have, let's say we have 3 parameters, xa, we seek 3 parameters, xa, xb. We seek 3 vectors, xa, xb, xc, where we have 3 givens, xa, xb, xc. And so xa will have to be xb wedged with xc dotted with 1 over xa wedged xb wedged xc. And xb will have to be minus xa. I'm going to take here, I'm just taking all the ABCs, the xa, xb, xc's, and wedging them together. And the one, our xa, has all those terms except for the, our x upper A has all those terms except for the x lower b in this wedge product. We omit that, but we have to toggle signs every time we move down the row. So we have xa wedged with xc minus dotted with xa wedge xb x wedge xc. And then xc will have to be plus xb, not xb, but the plus is minus minus because we're two terms down, xa wedged xb dot with 1 over the inverse of xa wedge xb wedge xc. So we can easily construct the geometric algebra form of our reciprocal frame vectors. And we see this works because if we take any, let's say x alpha, let's dot that with, let's just show this works by taking the dot product with x a. So we take xa dotted with x alpha for any alpha equals abc. And what do we get? We get x alpha dotted with x beta wedge x alpha bc and using distribution identity, that is just going to be x alpha wedged with xb wedged with xc all dotted with xa wedge xb wedge xc. So if alpha equals any of b or c, then this first term is 0. So only if alpha equals a do we get a trivector dotted with its inverse, which is 1. So we see that this equals delta alpha a. I guess we could put our a's upstairs. So that's why this works. So next time we're going to go through the computation of the reciprocal frame vectors using only matrix algebra, and we'll see that there is a simple structure to the reciprocal frame vectors in matrix algebra as well. We'll take the 2D example that we've just computed, and we'll see how that generalizes to higher dimensions. And that'll allow us to contrast the geometrical algebra form for the reciprocal frame vectors and the matrix algebra form for the reciprocal frame vectors. Specifically, we have a third way of computing reciprocal frame vectors that we're going to get to, which is using gradients of the parameters. And that method of computing the reciprocal frame vectors, we'll see that it's identical to the matrix algebra form, provided we are operating with a number of parameters equal to the dimension of the space. But that's a game for a different day.